Okay, this is one thing. And then with molybdenum disulfide, the idea is exactly the same. We have the same situation. Then in Valencia, we obtained many of the dichalcogenides, or at least 10, 20, 15 materials that are very big crystals. You see the crystals are more than centimeter size. Then for a chemist, these are, or for a coordination chemist, you cannot obtain this kind of materials usually. But well, in this kind of chemistry that you do in dry conditions, by chemical vapor transport with iodine, it's possible to obtain this kind of growing of a lot of materials that can be superconductors, semiconductors, or conductors. Then if we use the molybdenum disulfide in this kind of material, the molybdenum disulfide that is semiconductor in the ground state, well, when it's a single layer, then the coordination of molybdenum disulfide is, the molybdenum is trigonal prismatic, that is hexagonal H symmetry. Then when you react with butyl lithium to reduce this kind of layers, then to inject electrons in this kind of layers, you end up with 1T molybdenum disulfide. That means that the molybdenum disulfide changes from trigonal prismatic to octahedral site. And then in that case, you change also the transport properties, and then this one is metallic, this one is semiconductor. And then, okay, we can have this kind of layers, and to mix these layers with our nanoparticles of spin crossover, like before. Then this is one possibility. The other possibility is to do that, well, you can do that in solution, but you can do that also in a surface. First delaminating your system, and after putting butyl lithium. Then this is the other possibility, the other method, to make single layers of butyl lithium covered with these spin crossover nanoparticles. Okay, using the first process, well, this is the explanation. But well, what we did is we put spin crossover nanoparticles, which in that case, we cover the spin crossover nanoparticles to make them more stable with silicon oxide, with a shell of silica, a thin shell of 1 nanometer of silica that is possible. And in that case, the nanoparticles are quite stable at room temperature, well, at any temperature also, at 100 degrees centigrade also are stable. Then, because the previous one were not so stable, then in this case, these nanoparticles will react in solution, because if you use the spin crossover nanoparticles in solution without protecting with silicon oxide, the spin crossover are oxidized and are destroyed. Then you need to protect them. These nanoparticles, the size is around 20, 30 nanometers. Then these nanoparticles, well, you can observe here that the nanoparticles are formed by a shell of oxygen on the surface, or silicon oxide, and the iron is over all the nanoparticle. Then these nanoparticles, you react, well, first, what you do is you functionalize your molybdenum disulfide, put in some kind of nucleophilic agent with this kind of trietoxy iodine in which the iodine is leaving, and then in that case, you have this chain is connected to sulfur, and then you obtain a surface that is a trietoxy surface that is ideal to cover, to be reacting with silicon oxide. This trietoxy group, trietoxysilane group, is ideal to react with nanoparticles, and then we cover these nanoparticles with, well, the monolayers of our molybdenum disulfide with this kind of nanoparticles, and then we obtain, at the end, we end up with a system that we can measure by a squid the pure material, the nanoparticles of 70 nanometers, then, or the mixture of molybdenum disulfide with nanoparticles, and we obtain the hysteresis in two cases. And then what is interesting is not only the hysteresis, because the magnetic hysteresis is similar in the two cases. What is interesting is the transport. As I told you before, now, if you measure the transport, I told you this molybdenum disulfide is metallic, then I study this kind of transport, and the transport indicates also is sensitive. The transport of the molybdenum disulfide with pellets, for example, is not a single layer, but it's an assemble of single layers, it's a composite material. Then you observe that you are sensitive. Low spin and high spin are, when the system is undergoing transition between low spin and high spin, you are having this kind of hysteresis. Then the molybdenum disulfide is sensing now the properties of our nanoparticles, as in the case of graphene, but more easy because you do that in solution and not with a device. You can do that even in solution and measure with pellets, and you obtain also the same behavior. Okay, then nice. Then now I have finished. In this case, the take-home message for this kind of new heterostructures that are molecular 2D. Then so far people were studying heterostructures formed by 2D plus 2D or 2D plus 3D, whatever, but molecules combined with 2D is more new. Then this kind of combination can allow a molecular control. With taking a smart molecular system, you can control the properties of your 2D material. Then this is one idea, and I have shown you that it's possible to control the properties of graphene or molybdenum disulfide, putting on the top this kind of nanoparticles. Then this spin crossover complexes can allow the design of smart 2D heterostructures, as I have shown you. And then in this kind of materials, in the particular case, the 2D material can act as a sensor of the spin state. Then, as always, to have a sensor of a spin state is not so easy. As before I told you, in antiferromagnet, you need to have some indirect technique to detect the spin transition. Here, for having the spin state, you need also the help of the 2D material. The 2D material is helping us to detect the spin state, not only the color, but in the nanoscale you don't see the color of your material, but you can see a change in conductivity in the material, and this is very useful for in that case, sensing our spin state. Okay, then I have finished. Then these are the people that have been working. There are several students in red that have been working on the aspects of physics and chemistry and material science, and some tenure track researchers that I have in my group working with helping also these students to work on this topic. And all the collaboration I have had in this topic I have shown you today is with the University of Delft, with Gerre van der Sand and his group in particular. And then here I have the people that have been giving the money. Then thank you very much for your attention.